Hello, welcome to this video, Spinal Cord Repair, Part 4, Introduction to Signalling. Major part of this video will be looking at wiring up a spinal cord. So how will we do that? It's a pretty complicated piece of equipment, this spinal cord. For example, as I remember in previous videos, I showed you that the spinal cord, which is virtually the brain, extruded down a tube, roughly the size of this drinking straw. What sort of wires would I put in it and how would I wire it up? Now this drinking straw is a little bit short, so really it'll have to be about this long, which is a PVC tube, and run just from the top of your head to your tailbone. So what wires and how would I fit wires down here, and what signalling would I use to wire up a spinal cord? Also, these wires aren't really, the motor neuron is not really a wire, it's very close to a wire, so I had to choose an appropriate analogue that can represent a motor neuron. Also, we'll discuss that, how I picked an appropriate analogue to represent a motor neuron. It was quite a difficult choice, which also led me into the introduction to this motor neuron simulator. It uses this analogue to simulate a motor neuron, and it's quite a bit of complicated bit of equipment that I made, and it helps to educate the process and the operation of a motor neuron. We'll also talk about signalling and how wiring up different data signalling happens, and also we'll look at the correlation between a data cable and the spinal cord. Now they're very similar. Okay, so this is my dilemma. What analogue do I use to... Should I use semiconductors? Should I use bipolar, FETs, triacs, diacs, triacs, whatever? Should I use thermionics, pentodes, triodes, diodes? Or should I use electromagnetic, solenoids, relays, or motor uniselectors or uniselectors? What analogue do I use? So I thought about this. To teach you semiconductors, some people may be educated. That is probably 3 or 4 years education there. Thermionic valves, they have a very good analogue. They are a good analogue, but again, another 3 years and they're not used anymore. But electromagnetics, electromechanical, everyone sort of as a child played around with electromagnets. That is basically a coil, a wire with a piece of iron in the centre of it, and put a battery across it, and we have a solenoid. Now, I've thought about this. Very simple. Design everything around a solenoid. Use that as the analogue. So basically this is where we're coming from. So our next clip will be the Motor Neuron Simulator. Now this is a very complicated piece of equipment. It took me probably 3 years to design and probably $100,000 worth of investment in this device, and to teach you the understanding and the operation of this device is probably I don't know, another 20 videos. So we'll start with just an introduction to this the Motor Neuron Simulator. So I'll just bring it out now. So the next clip will be the Motor Neuron Simulator, and you'll just get an idea of the pathway we're going and how solenoids were used to simulate a motor neuron. Okay, so quickly, we've just established that our new analogue will be this solenoid, or in other words, an electromagnet. And today For simplicity, I'll introduce two neurological, whatever that word is, terms, and they'll be the action potential and the resting potential. So quickly, the Motor Neuron Emulator, simulator, whatever it is basically, let's swing this around, see if I can get a better shot. Looks something like this. Alright, I think we've got a better shot now of this motor emulator. I won't go into too much detail today. Many of the connectors are missing, but I can show you the action potential. There's various switches here that are used to simulate many of the conditions. Many diseases of the motor neuron, for example, motor neuron diseases, Alzheimer's, Parkinson's disease, multiple sclerosis. I can just switch this switch depending on the disease and I can simulate those conditions. Today we'll talk about this action potential, and basically that's just the travelling wave impulse along an axon of a motor neuron. So if you just look at these red LEDs here, and say for example I want to pull the muscle and lift my big toe, you'll see this travelling wave. So quickly it goes like this. I go to push my big toe or lift my toe, and you'll see these LEDs travel along, sending the message along down to the big toe. So again, we won't go too much into that. And we'll move now on to we'll go on to our solenoid and give you a bit more knowledge on the solenoid and how signalling comes evolved. Alright, so quickly here's our setup of our solenoid. Now we're operating with two 6-volt batteries in series through our switch through into our solenoid. So basically the current will go from the switch through the solenoid back through the batteries and to the other side of the switch. So when I operate this switch, you'll see the solenoid operate. There you go, see that operating. Now, this is a 12-volt solenoid, so theoretically it shouldn't operate if I switch out one of the batteries. So let's see what happens. There you go, it dropped out. So it'll only operate with 12 volts. So let's go to the next stage now and start looking at this. We're talking about action potentials. Right, I've set the solenoid up with a voltmeter and a variable power supply that we can clearly see demonstrate these so-called two voltages that we're actually interested in the motor neuron, which is the resting potential and the action potential, or action voltage and resting voltage. As we know, our solenoid is a 12-volt solenoid, so if I apply 12 volts to it, it'll operate, and that will be our action potential. The voltage you'll be interested in is our resting voltage. So let's wind the solenoid back. Now we'll increase the voltage until we see this solenoid. There we go, 8.9 volts. So that's operational. Now the resting voltage would be that midway point where the solenoid would be in equilibrium. So let's just find that. So just back this off a bit. There we are there at 7.5. The solenoid is in equilibrium. It can stay in halfway position, which counteracts the pressure of the spring. So therefore this is the resting voltage at 7.5, and our action voltage is 12 volts. So as we can write that in now. Right, summing up our voltages, here's our action voltage, 12 volts. We'd operate the device at normally 12 volts. This gives our full operational strength. Obviously as we get a bit older, if this is referring to a neuron cell, the voltage would drop probably 5% after it 60 years of age. I don't know roughly the figures. The resting voltage, as we know, was this 7.5, which is that equilibrium voltage, and just added in that extra voltage. The just operate voltage was that anything below that and the device won't operate. So I'm assuming if you're very, very old, your voltage for your operational voltage for your motor neurons would get down around about this level, if we can use this analogy. That being said, as I said, if you refer back to the small video I made on the placenta and how the brain and the body are two different animals, the brain, in later videos we'll find out why it is actually protected by this placenta, and it in fact goes to a lot of trouble to isolate itself from the body, because these voltages are very important. Unlike a normal cell voltage, which we'll learn about in a few more episodes, is not as critical. Like if we're referring to a skin voltage, the voltage in a skin cell, the resting voltage, you'll still function in your old age with a decreased voltage operation. But right now we'll move on to the next section. Okay, I've just brought back the solenoid and our simple circuit. Remember our 12 volts and our switch, and let's start getting this thing to an application similar to the spinal cord. Okay, back in the early 1800s, when the use of electricity was evolving, one of the applications was a buzzer, which works on a solenoid, and would start off with something like a 10-story building where someone on the top floor would need to contact someone in the mail room to come up and pick up some mail, so they would throw a switch and the buzzer would ring and someone would come up and get the mail. So save running down the stairs. So that was the first application. So let's move on a bit more. Let's start evolving a bit more and increase the intelligence of our signalling. So let's start moving up closer to what the spinal cord works like. Right, 1832, things changed. A man by the name of Morse developed this telegraph, and our signalling became a little more sophisticated. So remember, our mail room, we press the button to send the signal for the mailroom boy to come and get the mail, except he's gone to lunch. So we need to signal back and tell the person at this end he's gone to lunch and he won't be back for a few hours. Right, we have to get a bit more sophisticated. Right, solution was telegraph system both ends. Send the mail boy up. He's at lunch. Okay, simple signalling, easy. Thanks to Mr. Morse. Okay, let's start bringing back our analogy to the spinal cord. The 10th floor to the basement where the mailroom is about a nerve impulse about from your brain to your eye, if that. Very short distance. In proportion, our motor neurons travel huge distances, hundreds of kilometres, like the telegraph system between two towns. So we are going to encounter the same problems with our spinal cord as it is transmitting a signal over long distances. So remember that back in our telegraph days we had things called the telegraph line. It strung between poles, which would go possibly 100 kilometres between towns, and two operators would signal, and using this Morse code system, which was dashes and dots, and no problem. People worked out systems, and The first thing they encountered was number 1. Let's move on to number 1 problem. Okay, problem number 1, wire resistance. As we know, the longer we go with our signal, the more the resistance of the wire will actually affect our signal to the point where the resistance will be so great that it won't operate our buzzer at the other end. So what was the solution? Thicker wire. Let's use nice big thick wire. Great idea. Yep, okay. So, only problem is low resistance, it'll carry further, but it costs a fortune. So that's not a solution, and it's not going to fit in our spinal cord. Right, solution. Make the receivers more sensitive. Make them as sensitive as you can get. And they made the receivers very sensitive, and they found out the wire, about number 8 fencing wire, which is about the thickness of a coat hanger, was ideal. It would string between the poles, not sag. Ice, snow and whatever could land on it, and it never broke. So that was their solution. Till they realised they come across another problem. Problem number 2, which also affects the spinal cord. Same problem. Problem number 2, number of wires. As we got more telegraph systems going on, we actually needed more wires, so we string more wires between the poles. And it came to a point where we were just overloading these poles with more and more wires. We had to put more and more cross beams. And as you know, if you look back in the old photographs of early telegraphs going through our cities and that was just a cobweb of wires in the sky. So we had to find a way of reducing the number of wires. So how do we solve that? Here we go. Right, the solution was, let's use the earth for our other conductor. So as we know, the earth is a brilliant conductor. It's the equivalent of a big piece of copper wire buried under the ground. So what they did is they strung one wire along the poles, and they used the other wire down at the ground. And that was the solution. Reduced our number of wires by 1, and the economics was much better. But there was another problem. Right, the problem was, number 3, what wire goes to Earth? Do we make the positive go to Earth, or do we make the negative go to Earth? Now, it's a no-brainer, in fact. The actual planet, this planet that we're on, it is positively charged. So everything on the ground is positive, everything above the Earth, the air, the sky, is negatively charged. So what they did was they just made it the same voltage potential as the Earth, positive. Right, which leads us back to our spinal cord. The creator, was a no-brainer for him. Same thing. He made the other conductor in our spinal cord positive, which is the earth potential, the outside of the ground, the same potential. And that's why our spinal cord has a positive earth. Alright, we think we've sorted out our problems, but as we know, there's another one comes up. Okay, this is our single wire signaling system and our earth return. Everything's working fine. And in the telegraph days, this was perfect because we had two operators, Fred and Bill. Now, Fred and Bill have got brains. So this is actually an intelligent system. It's got a level of, I guess, a protocol above normal single wire. So it's moving up to an intelligent system. Now, what would happen is, quickly, these operators were so attuned to the signalling that they knew who was on the other end, because each person had their own unique identifier the way they press the key. Now, what would happen is that because this overlaying intelligence protocol with two people with brains, they could actually predict what was happening or from the conversation, You didn't have to complete sentences in many cases. So a typical situation would happen where Fred would send Bill, I've got a passenger who's needs getting on the train and blah blah blah. Can you give him a Helen? And Bill sees this conversation's long. He knows where it's going and he starts writing down things. But the train all of a sudden gets derailed in the middle of the conversation. Now, Fred is sending, and Bill says, heck, I've got to send him quickly, tell him that the train's crashed. Fred goes, hey, whoa, hey, Bill must want to send something to me. The train's derailed. So, because it's an intelligent system, the two brains can actually compensate for the weakness in the one wire signalling. Now, that doesn't happen with the spinal cord. We can't use our brain. Your big toe says, oh, I don't want to move today, or doing something, and the brain's got to say, oh, I've got to drop everything and figure out what's going on with this big toe. You can't do that. So our spinal cord is somewhat a little bit unintelligent with our protocol. So that leads us to another way of overcoming this problem. Right, just before we go on the solution, let's just go over the circuit of our little device here, which is our little Morse code transmitter receiver. And as we know that both the receiver and the transmitter are in the one unit here. So this is the circuit of it. So basically, when I close this switch, the current flows around here and makes this buzzer work, and at the same time goes up here, around here, and makes this buzzer work. And we share, as we said before, with our common ground. We can now make this positive. We've established this should be ground, and it can actually be buried in the ground. We don't have to have a wire, but we use this common wire here for both going in this direction and in this direction. So therein lies our problem, which is okay when we have two intelligent people at the other end, Fred and Bill with brains to interpret that the signal is going either end, but we can't do that if we haven't got the intelligent system. So let's just move on to the solution. Right, so let's redraw the circuit. We know this is a common earth, so we can just remove this wire and redraw it down here. So now, to do our simple signalling, we have three wires. We have our common earth, and our transmit wire, and our receive wire. So, unlike this system, which we shared one wire to do both. So this system is called, if you go into data signalling, it's called single duplex, and this is called full duplex, which send and receive directions are isolated. Okay, so I think we're getting very close now to showing what the circuit of the cabling would look like in the spinal cord. Okay, so a little bit more complicated. We're going to start putting some more wires into this circuit. So here we have our brain. All these wires leave our brain and go to the various parts of our body. Here I have three receivers, one from the y-axis of the middle ear, and one from the eye, and one from the nerve in the big toe. So the brain says move big toe, and a signal goes down to the big toe to move it. So just some of the protocol and some of the computing that's involved will be the big toe nerve says yes, I'm on the ground, you can activate me. The y-axis in the middle ear will say yes, he's upright and he's in balance, go ahead, start moving. And the brain will interpret this, but then the eye says hang on, stop, sends a signal to the brain, stop everything, he's on the edge of a cliff, don't move. So the brain has to interpret all these signals, just a few, and all these signals go down this little tube. So now let's have a look what a typical cable might look like, which may give us a representation of how the spinal cord may be wired. Right, now here's what a typical data cable would look like. Usually they have a plastic PVC sheath that goes around the outside. Next you'll have a protected braiding shield, which is a Faraday shield, which stops inductive interference. And also running and touching this braided copper shield is our common earth wire, and that's usually there, that single uninsulated wire. Next you'll find is some sort of plastic wrap that binds and holds all the wires together. Now in this case here we just have about 25 wires on, and in the spinal cord there'd be hundreds of thousands, but each individual wire would be common to this common earth to make our circuits, whether in a transmit or a receive direction. And if we're talking about the spinal cord, those hundreds of thousands of wires will be fitting down this straw. So basically that's what, very similar to what the spinal cord will be composed of, a data cable. Right, here we go. We're going to just do a bit of a summary here. So we obviously looked at how we could wire up this spinal cord, which was, you end up with this similarity between the two, the data cable and the spinal cord. We can see it evolving. We also picked up on this analog, and we brought in two neurological terms. This action potential voltage and the resting voltage, which are just a really slight introduction to neurological terms. And I touched on a little bit about old age and how cell voltages, the voltage deterioration can affect that. But our main core of our video is this signalling. A lot of diversion on that, because that's will take us into our next higher levels. This becomes more and more complicated, and I'll be bringing out our Motor Neuron Simulator more and more to help us achieve higher levels of understanding. But at this stage, this is a very simple introduction. So anyway, hopefully you've sat through this, and it's quite a long video, but these are educational videos. They're not out there for entertainment. As you know, people come to these to find out information. So hopefully you've got what you needed and we're inspired to go to the next one. So thanks a lot for watching.